In this video, I'll cover probabilistic CCG parsing. I'll start out by describing combinatory categorial grammars in general, followed by a brief discussion of ambiguity in CCGs. Then I'll close by talking about some parsing frameworks that can be used to produce CCG parses. We talked in the last video about lexicalized context-free grammars. An example of a really lexicalized grammar is the combinatory categorial grammar. CCGs group words into categories based on a comprehensive lexicon, and then define different ways that those categories can be combined to form effective input parses. There are three main parts to a CCG: the categories, the lexicon, and the corresponding rules. CCG categories can be either atomic elements, so things like a basic noun phrase or sentence unit, or single argument functions, assuming that the arguments are valid categories themselves. There are two types of single argument functions that you'll see in CCG notation. An x followed by a forward slash followed by a y means that the function seeks a constituent of type y to the right and returns constituent x. An x followed by a backslash followed by a y means that the function seeks a constituent of type y to the left and returns constituent x. The CCG lexicon is what then assigns those CCG categories to different words. So it might assign a word like Chicago to the atomic category of a noun phrase, and it might assign cancel to the functional category that represents a transitive verb. The CCG rules then specify how these different functions and their arguments can be combined. There are two main rules that can be applied to functions: the forward function application and the backward function application. The forward function application applies the specified function to its argument on the right, resulting in the specified category. The backward function works very similarly, but it applies the specified function to its argument on the left, resulting in the specified category. Beyond those two functions, there's also a coordination rule that can be applied. This rule basically says that two categories of the same type can be conjoined to form a new single instance of the same type. We can see how a CCG could then be applied to parse a very simple input, shown here. We start out by assigning categories to the words based on the CCG lexicon. Then we can go ahead and do a forward application for the functional category for the word serves, since there is indeed a noun phrase to the right. Now that we've done our forward application, we can go ahead and do a backward application, since there's a noun phrase to the left of this new constituent, and that's what we're looking for. So since now we've matched a full sentence unit, we can see that we had a successful categorial grammar derivation for the input phrase. There are several useful operations that can also be applied to functions in CCGs, which allows for more advanced derivations to be generated. Forward and backward composition allows you to combine functions with one another. In forward composition, given two functions in which the first seeks a constituent of type y to the right and the second provides a constituent of type y as its result, you can compose them together such that the resulting function produces the type of the first function while accepting the argument of the second function. Backward composition is very similar, with the only difference being that the first function seeks a constituent of type y to the left instead of the right. Type raising is another useful operation in which you can convert atomic categories to functional categories, or simple functional categories to more complex ones. Basically, you take the original category and convert it to a function that seeks as an argument a function that takes the original category as its argument. Type raising is nice for when you want to represent complex constituents and can create opportunities for more accurate derivations. When combined together with function composition, it is often easier to effectively parse long-range dependencies. Just like tree banks exist for phrase structure parses, they also exist for CCG parses, and the availability of these resources is crucial for the development of probabilistic CCG parsers. The largest CCG tree bank is CCG Bank. It's based on the Penn tree bank and includes a 44,000 word lexicon with more than 1,200 categories. Since there are so many lexical categories in CCGs, this can lead to ambiguities when parsing. A given word could potentially be associated with many different categories. This means that the main issue that needs to be addressed in CCG parsing is resolving the choice of which lexical category to assign to a word, rather than focusing primarily on grammar rules. Probabilistic CKY can still be applied for CCG parsing, but in order to work effectively, it needs to be adapted a bit. Otherwise, there would be a huge number of constituents added to the table for each word, and the vast majority of those constituents would be irrelevant to the desired parse. The solution to this problem is to identify which lexical categories are most likely for a given word and work only with those. This process is referred to as supertagging, and supertags are useful not only for probabilistic CKY, but also in other CCG parsing frameworks. Supertagging is generally framed as a supervised sequence labeling problem. A model is trained on a CCG tree bank, such as CCG bank, to predict the allowable category assignments or supertags for each word in a lexicon, given an input context. After extracting these supertags, the selected parsing algorithm can proceed more or less as usual. So as already mentioned, we could use probabilistic CKY, or another popular CCG parsing technique is to make use of the A-star algorithm. We won't cover the A-star algorithm in detail in this course, but you'll probably encounter it in other courses like algorithms or AI. A-star is a heuristic search algorithm that finds the lowest cost path to an end state, in our case that would be a parse, by exploring partial solutions along the way and following the lowest cost option at each iteration. The search states, when using A-star for parsing, are edges representing completed constituents, and the cost is based on the probability of a CCG derivation occurring. A-star results in fewer unnecessary constituents being explored than probabilistic CKY, making it an efficient and effective alternative for CCG parsing.